What's the difference between a struggling data scientist and a thriving one? It's not fancy algorithms, it's mastery of data wrangling. While everyone focuses on the glamorous parts of data science, the professionals know success happens before a single model is trained. In this comprehensive tutorial, I'll walk you through the entire EDI framework for transforming chaotic datasets into clean, analysis-ready data. You'll learn practical solutions for missing values, outliers, and inconsistent formats that can derail even the most promising projects. When you picture a data scientist's job, what comes to mind? Complex machine learning algorithms, beautiful interactive visualizations, neural networks making sophisticated predictions. While these elements make for exciting LinkedIn posts and YouTube thumbnails, they represent just a small fraction of what real data work involves. If you've been focusing your energy on mastering the latest deep learning frameworks or visualization libraries, you might be shocked to learn what industry surveys have uncovered. Data professionals aren't spending most of their time building models or creating dashboards. The reality? Between 60% and 80% of a data scientist's working hours are consumed by something far less glamorous: data wrangling. That's right. For every hour spent training an algorithm or fine-tuning a model, data professionals spend 3 to 4 hours cleaning, transforming, and preparing data. This stark contrast between perception and reality creates one of the most significant disconnects in the data science field today. Look at how data science is typically taught and presented online. Course syllabi emphasize statistical methods, algorithmic approaches, and visualization techniques. Tutorials walk through building models using pristine pre-cleaned datasets. Social media celebrates breakthrough algorithms and stunning visualizations. But the messy, unglamorous reality of preparing data for analysis remains largely invisible. This invisibility is particularly problematic because it creates a dangerous skills gap. Many aspiring data scientists develop strong theoretical backgrounds in statistics and machine learning while remaining underprepared for the day-to-day reality of working with messy, incomplete, inconsistent, real-world data. The educational system bears much of the responsibility for this disconnect. One industry expert noted that students often learn statistical analysis with clean datasets, which does not reflect real-world challenges. This sanitized approach to education creates a false impression of what data work actually entails and leaves graduates unprepared for their first professional roles. Think about standard classroom exercises or online tutorials. They typically begin with a neat rectangular data set where all values are properly formatted, missing data has been handled, and variables are clearly defined. This approach makes sense for teaching specific concepts, but it sidesteps the complex reality of actual data work. It's like teaching someone to drive by, starting them in a car that's already moving at highway speed. The consequences of inadequate data wrangling skills extend far beyond individual frustration. Poor data preparation undermines even the most sophisticated analyses through the classic garbage in, garbage out principle. When data contains undetected errors, inconsistencies, or biases, these problems propagate through the entire analytical pipeline, compromising the validity of any conclusions drawn. Consider a simple example: a dataset containing customer information where some entries include postal codes with spaces like AB123CD, while others don't, AB123CD. To a human, these clearly represent the same information, but to an algorithm, they're entirely different categories. Without proper standardization, any analysis broken down by location will produce misleading results. Or Imagine time series data where timestamps are recorded in different time zones without proper documentation. Patterns that appear to show interesting periodic behavior might simply reflect time zone differences rather than actual phenomena in the underlying process being studied. These examples only scratch the surface of the countless ways messy data can undermine analysis. The more complex and diverse your data sources, the more critical proper data wrangling becomes. This explains why data wrangling has earned the ominous nickname the silent killer of projects among seasoned professionals. Despite its critical importance, data wrangling continues to receive minimal attention in training programs and tutorials. This neglect leads to significant project delays and failures that could be avoided with proper preparation techniques. To address this gap, data professionals need a systematic approach to transform chaotic data into analysis-ready datasets. This is where the EDI framework proves invaluable. Originally developed for instructional design, EDI has been adapted for data wrangling to provide a structured methodology for handling messy data. EDI stands for Analysis, Design, Development, Implementation, and Evaluation. In the context of data wrangling, analysis involves thoroughly examining your dataset to identify quality issues, inconsistencies, and structural problems. Design means creating a systematic plan for addressing the identified issues, selecting appropriate tools and techniques. Development represents the actual implementation of data cleaning and transformation operations. Implementation involves applying your developed wrangling workflow to the full dataset. Evaluation entails assessing whether your data preparation has successfully addressed the identified issues without introducing new problems. The iterative nature of this framework is particularly valuable for data wrangling, as data cleaning is rarely a linear process. New issues often emerge during cleaning that require revisiting earlier steps. Let's look at what happens when data wrangling is neglected or performed inadequately. Consider a retail company analyzing customer purchasing patterns to optimize inventory. Their dataset includes transaction records from multiple systems collected over several years. Without proper wrangling, the analysis might miss critical insights or worse, lead to actively harmful decisions. Suppose some store locations recorded purchase times in 12-hour format with AM/PM indicators, while others used 24-hour format. Without standardization, analysis of purchasing patterns throughout the day would be meaningless. Or imagine product categories that were inconsistently labeled across different systems. Women's footwear in one system might be ladies' shoes in another. Without reconciling these differences, any category-based analysis would be fundamentally flawed. These problems multiply when working with data from disparate sources. Combining internal transaction data with external market research, social media sentiment, or economic indicators. Each additional data source introduces new formatting, structural, and quality issues that must be addressed before any meaningful analysis can occur. The consequences of inadequate data wrangling extend beyond the immediate project. In organizations where data and insights are shared across teams, poor data preparation creates a contamination effect, where flawed analyses based on inadequately prepared data influence decision-making throughout the organization. This is why data wrangling deserves to be called the silent killer of projects. Unlike a dramatic technical failure that's immediately apparent, problems stemming from poor data preparation often remain hidden until they've caused significant damage. A model might appear to perform well on test data but fail in production. Insights might seem compelling but lead to poor business decisions. These failures aren't typically attributed to their true cause, inadequate data preparation, perpetuating the cycle of underinvestment in data wrangling skills and processes. Breaking this cycle requires recognizing data wrangling for what it truly is, not just a preliminary step to be rushed through, but a foundational process that determines whether your analysis will yield valuable insights or misleading conclusions. While most data science education treats data wrangling as a single checkbox to complete, this oversimplification explains why so many projects fail. The truth, data wrangling breaks down into three critical phases: importing, tidying, and transforming. And mishandling any one of them can compromise your entire analytical pipeline. What's particularly deceptive about data wrangling is that these three phases seem straightforward on the surface. In reality, each contains numerous decision points and technical challenges that experienced data scientists navigate instinctively, but beginners often stumble through without realizing the consequences of their choices. Let's start with the importing phase. This initial step involves bringing data into your analytical environment from external sources. Whether you're working with Excel spreadsheets, CSV files, or connecting to databases, this first touch point with your data sets the foundation for everything that follows. In the Tidyverse ecosystem, importing typically involves converting your data into what's called a tibble format, a specialized kind of data frame designed for modern R programming. But importing isn't just about loading files, it involves critical decisions about how to interpret the data structure. When your CSV file uses semicolons instead of commas as separators, how should those be handled? What about encodings for special characters or date formats that vary by region? Each of these seemingly minor details can dramatically affect how your data is interpreted. Consider a scenario where your data set contains dates. If your importing process incorrectly interprets European format dates, day, month, year, as American format, month, day, year, every subsequent analysis involving time will be fundamentally flawed. Even more insidious, this type of error might not become apparent until months into a project when seasonal patterns suddenly don't make sense. The second phase, tidying data, is where many of the most complex challenges emerge. Tidying involves restructuring your information into a consistent format, where each variable forms a column, each observation forms a row, and each type of observational unit forms a table. This seemingly simple principle becomes remarkably complex in practice. Tidying addresses inconsistencies in how information is formatted and structured. Perhaps some of your temperature readings use Celsius while others use Fahrenheit without clear labeling. Maybe product categories are inconsistently capitalized or use different naming conventions across systems. Your dataset might contain missing values represented in multiple ways: NA, null, empty strings, or even special values like 999 that were used as placeholders. The tidying phase involves detective work and methodical problem solving. You'll need to standardize formats, handle missing data appropriately, and ensure consistent representation across your dataset. This is where you'll reconcile disparate data sources that might describe the same information in completely different ways. One particularly challenging aspect of tidying involves restructuring data between what's known as wide and long formats. Many statistical analyses and visualizations require data in specific structures that differ from how the information was originally collected or stored. Mastering these transformations is essential for effective analysis. The third phase, transformation, is where you begin shaping your now consistently formatted data into the specific structures needed for your analysis. This involves selecting relevant variables, filtering observations based on criteria, creating new calculated fields, and aggregating information at different levels. Transformation is the bridge between raw data and actionable insights. Here, you might calculate growth rates from raw sales figures, create categorical variables from continuous measurements, or derive entirely new metrics by combining existing fields. You might need to normalize variables to make them comparable, or apply mathematical transformations to address skewed distributions. For example, if analyzing customer behavior, you might transform individual transaction records into customer-level metrics like average purchase value, frequency, and recency. Or when working with geographic data, you might need to transform coordinate systems to calculate accurate distances between points. What makes the transformation phase particularly challenging is that it's highly dependent on your specific analytical goals. The same data set might require completely different transformations depending on whether you're building a predictive model, creating visualizations, or performing statistical tests. These three phases, importing, tidying, and transforming, form an interconnected workflow. In practical data science, using the Tidyverse ecosystem, you'll seamlessly move between them using a series of functions connected with the pipe operator. %. This creates readable, maintainable code that clearly documents how your raw data becomes analysis-ready information. Now, here's what many tutorials don't emphasize enough. Skipping or rushing through any of these phases creates compounding problems throughout your analysis. These problems typically manifest in ways that are difficult to trace back to their source. For instance, if during importing you fail to properly handle text encodings for non-English characters, you might find yourself with corrupted text data that makes natural language processing impossible later on. If during tidying you don't properly identify and handle outliers, your statistical models might produce wildly inaccurate predictions. And if during transformation you create derived variables without documenting your methods, future analysts, including yourself, 6 months later, may misinterpret what those variables actually represent. The compounding nature of these errors means that small oversight in early phases can completely invalidate complex analyses performed later. This is why experienced data scientists often approach data wrangling with methodical care that might seem excessive to beginners, but is in fact essential for reliable results. Each of these three phases contains numerous sub-processes that require deep understanding. The importing phase involves not just reading files, but understanding character encodings, data types, and handling large datasets efficiently. The tidying phase includes techniques for detecting and addressing missing values, standardizing inconsistent formats, and restructuring data into analysis-ready forms. The transformation phase encompasses everything from basic filtering and selection to complex window functions and relational operations across multiple datasets. What's particularly challenging for beginners is that many of these sub-steps aren't immediately obvious when working with example datasets in tutorials. Those carefully curated examples rarely contain the messy complexity of real-world data. As a result, new data scientists often develop workflows that work perfectly for clean examples but collapse when faced with actual business data. The difference between mediocre and exceptional data analysis often lies not in the sophistication of machine learning algorithms employed, but in the thoroughness and care applied to these three phases of data wrangling. Master data scientists understand that the quality of their insights depends entirely on how effectively they navigate the countless decision points within importing, tidying, and transforming their data. Even the most meticulous data wrangling process can save you if you fail to detect fundamental problems lurking in your data set. The most dangerous data issues aren't the obvious errors that crash your code, but the subtle inconsistencies that produce plausible yet completely wrong results. These hidden problems are particularly insidious because they often go undetected until they've already contaminated your analysis with misleading conclusions. This is where the analysis phase of the EDI framework becomes critical. Before you can fix problems in your data, you need a systematic approach to diagnose them, essentially performing a comprehensive health check on your dataset before proceeding with any transformations or modeling. Let's start with one of the most pervasive challenges, missing data. What many data scientists don't realize is that missing values aren't all created equal. They fall into three distinct categories that require fundamentally different handling approaches. Missing, completely at random, MTR, represents true randomness. These values have no relationship to any other variables in your dataset. When data is missing at random, MAR, the missingness is related to observed variables, but not to the missing values themselves. For example, older participants in a study might be less likely to answer certain questions, but their age, which you know, explains the pattern rather than the actual missing values. The most problematic category is missing not at random, MNR, where the missingness directly relates to unobserved data. Imagine a salary survey where high-income individuals systematically refuse to disclose their earnings. The very value that's missing explains why it's missing. This distinction matters tremendously because treating MNR data as if it were MCAR can introduce significant bias into your analysis, potentially leading to completely invalid conclusions. To identify these patterns, you'll need to examine relationships between missing values and other variables in your dataset. Heat maps highlighting missing data patterns across variables can reveal systematic relationships. Correlation analyses between missingness in one variable and values in others can help distinguish between MR and MCAR scenarios. The diagnosis of the missing data type isn't just an academic exercise. It directly determines which imputation strategies will be valid for your analysis. Outliers present another diagnostic challenge that requires careful examination. Statistical approaches like the z-score method can help identify values that deviate significantly from the mean. By calculating how many standard deviations a point falls from the mean, you can establish thresholds, commonly 3 standard deviations, beyond which data points are flagged for review. For skewed distributions, the interquartile range IQR method often proves more robust. This approach identifies outliers as values falling below Q1, 1.5 IQR or above Q3 plus 1.5 IQR, effectively highlighting points that lie well beyond the middle 50% of your data. However, statistical detection is only the beginning. Visualization techniques like box plots, scatter plots, and histograms provide crucial context that pure numbers might miss. A data point might be statistically unusual yet perfectly valid within the domain context. For instance, a spike in website traffic during a major product launch may appear as an outlier statistically, but represents a legitimate business phenomenon rather than an error. This is where domain expertise becomes invaluable in distinguishing between actual errors and meaningful anomalies. Structural errors in datasets can be even more challenging to detect because they often masquerade as valid data. Inconsistent date formats represent a classic example. Some records might use MM, DD, YYY, while others use DD, MM, YYY. Without proper detection, January 3rd and March 1st become indistinguishable, creating temporal chaos in your analysis. A systematic approach involves profiling date fields to identify inconsistent patterns and potential ambiguities before they contaminate time-sensitive analyses. Duplicate records present another structural challenge. They can artificially inflate certain statistics while undermining the validity of others. While exact duplicates are relatively easy to catch, partial or fuzzy duplicates, like the same customer entered with slight variations in name or address, require more sophisticated detection techniques. These might include calculating similarity scores between records based on key identifying fields, or using probabilistic matching algorithms to flag potential duplicates for review. Beyond these specific issue types, a comprehensive data quality assessment should examine multiple dimensions systematically. Completeness measures the degree to which all required data is present, not just checking for nulls, but ensuring that the dataset contains all expected observations and variables. Consistency verifies that related data elements maintain logical relationships across the dataset. For example, if a customer's age is 25, their birth year should align with that value within an acceptable margin. Validity examines whether data conforms to defined formats, ranges, and business rules. This might involve checking that email addresses contain the @ symbol, postal codes match regional patterns, or numerical values fall within physically possible ranges. Accuracy, perhaps the most challenging dimension to assess, evaluates whether the data correctly represents the real-world entity or event it describes. This often requires cross-validation against external reference data or internal consistency checks. To implement this comprehensive assessment systematically, you can develop a data quality checklist customized to your dataset and analysis goals. This checklist might include 1. Distribution analysis for each variable to identify potential outliers, impossible values, or unexpected patterns. 2. Missing value analysis to quantify and characterize patterns of missingness. 3. Format consistency. Checks across date, numeric, and categorical variables. 4. Duplicate detection at both the record and variable level. 5. Relationship verification between logically connected variables. 6. Cross-validation with historical or external reference data where available. 7. Assessment of temporal consistency for time series data. By applying this checklist systematically before diving into data transformation, you create an early warning system that catches potential issues before they can contaminate your analysis. This diagnostic process might seem time-consuming, but it's far more efficient than discovering fundamental data problems after you've already built models or generated reports based on flawed foundations. Remember that data quality issues rarely exist in isolation. A data set with inconsistent date formats is likely to have other structural problems as well. Similarly, patterns of missing values often correlate with outliers or validity issues in related variables. This interconnectedness means that a holistic diagnostic approach will generally uncover more issues than investigating each dimension separately. The importance of this systematic problem detection becomes even clearer when you consider the cascading nature of data errors. A seemingly minor issue, like a few missing values or inconsistent decimal precision, can proliferate throughout your analysis pipeline, affecting derived variables, model parameters, and ultimately business decisions. What begins as a small data quality issue can end as a significant analytical error with real-world consequences. The good news is that once properly diagnosed, most data quality issues can be addressed with appropriate techniques. The key is identifying them early, understanding their nature completely, and documenting both the problems and your approach to handling them. This documentation creates transparency in your analysis process and allows others to evaluate the potential impact of data quality issues on your conclusions. Documentation creates transparency, but what tools actually make your data wrangling process both transparent and efficient? The difference between spending all day cleaning data versus finishing in time for lunch often comes down to one critical ecosystem of tools that most analysts overlook until they're drowning in messy data. This is where the Tidyverse transforms your approach from reactive firefighting to strategic data preparation. The design phase of the EDI framework is where you create a systematic plan to address all those data quality issues you identified during analysis. Think of it as architecting a solution before writing a single line of code. Without this deliberate design step, most analysts fall into inefficient patterns that waste hours of precious time. Consider a typical ad hoc data cleaning approach. You notice a problem, write some code to fix it, spot another issue, write more disconnected code, and repeat this cycle endlessly. Each fix exists in isolation, creating a fragmented workflow that's difficult to understand, maintain, or reuse. What's worse, this approach often introduces new errors while fixing old ones, as changes in one part of your code affect data used elsewhere. The Tidyverse offers a fundamentally different paradigm. Rather than a collection of disconnected functions, it provides an integrated ecosystem of packages that work together seamlessly to transform your data wrangling workflow. Each package has a specific purpose in the data preparation process, but they're designed to function as a cohesive unit. At the core of this ecosystem is the pipe operator %%, which revolutionizes how you structure data wrangling code. Instead of nesting functions within functions or creating numerous temporary variables, the pipe allows you to chain operations in a logical sequence that mirrors how you'd verbally describe your data preparation process. Let's compare the difference. Traditional R code might look like this. With the pipe operator, this transforms into the second approach reads like a clear set of instructions. Take this data, filter it, arrange it, and select these columns. The flow is intuitive, eliminating the need to track multiple intermediate objects and making the code dramatically more readable. This isn't just about aesthetics, it fundamentally reduces cognitive load, allowing you to focus on the logical flow of your data preparation rather than the mechanics of the code itself. The Tidyverse consists of several specialized packages that each handle a specific aspect of data wrangling. Let's explore the key components. Reader focuses on importing data efficiently. Unlike base R functions that often make unwanted assumptions about your data, like converting strings to factors, Reader gives you precise control over how your data is imported. It's designed to be both faster and more predictable than base R equivalents, parsing even large files quickly while respecting the structure of your data. Dplyr is the workhorse for data transformation. Its vocabulary of functions, filter, select, mutate, summarize, and arrange maps directly to the most common data manipulation tasks. These verbs are intuitive and consistently structured, making your code more readable and reducing errors. For example, filter focuses exclusively on row selection, select A on column selection, and mutate on creating or modifying variables. Tidyr specializes in restructuring data between formats. It implements the principles of tidy data, where each variable forms a column, each observation forms a row, and each type of observational unit forms a table. Functions like pivot longer and pivot wider Make it simple to transform between wide and long formats depending on your analytical needs, while separate and unite help with splitting or combining information within columns. Per extends the Tidyverse's capabilities for iteration and functional programming. When you need to apply the same operation across multiple datasets or columns, Per provides elegant solutions that avoid repetitive code. Its map, family of functions, allows you to express complex iterative operations clearly and concisely, further enhancing code readability and maintainability. Together, these packages create a comprehensive toolkit for data wrangling that's greater than the sum of its parts. The consistent design philosophy across the Tidyverse means that once you learn the principles of one package, the others become much easier to understand and implement. But the Tidyverse isn't just about individual tools, it's about how they integrate into a reproducible workflow. One of the most powerful aspects of a well-designed Tidyverse approach is modularity. Rather than writing monolithic scripts that are tied to specific datasets, you can create reusable functions that encapsulate common data cleaning patterns. For instance, if you frequently work with datasets that contain similar issues, like inconsistent date formats or specific patterns of missing values, you can design functions that standardize your approach to these problems. These functions become building blocks that you can assemble in different configurations depending on the specific challenges of each new data set. This modular approach offers several advantages. First, it reduces redundancy. You write the solution once and apply it consistently. Second, it improves reliability. When you fix a bug in a function, that fix propagates to all uses of that function. Third, it enhances maintainability. Your code is organized around logical units rather than scattered across scripts. Documentation is another critical element of the design phase that the Tidyverse facilitates. Clear comments in your code explain not just what you're doing, but why you're making specific choices. This creates transparency in your data preparation process and ensures that others, including your future self, understand the rationale behind your decisions. These comments explain both the what, converting abbreviations, and the why, consistency with other data sets, including a reference to the lookup table used. This level of documentation is invaluable for reproducibility and knowledge transfer within teams. Version control systems add another layer of documentation by tracking changes to your code over time. This creates a historical record of how your data preparation approach evolved, which can be critical for auditing purposes or when tracing the origin of unexpected results. The Tidyverse also embraces the use of tibbles, an enhanced version of traditional data frames. Tibbles provide better printing in the console, showing only the first few rows and columns that fit on your screen, don't automatically convert strings to factors, and give more informative error messages. These features make your data exploration and debugging process more efficient, further streamlining your workflow. What makes the Tidyverse particularly powerful is its consistent naming conventions. Function names clearly indicate their purpose. Arguments follow predictable patterns across packages, and the overall design philosophy prioritizes clarity and readability. This consistency reduces the cognitive load of switching between different parts of your data preparation workflow, allowing you to focus on solving problems rather than remembering syntax. The consistency of the Tidyverse helps you focus on solving problems rather than remembering syntax, but there's one data problem that requires special attention beyond any tool's capabilities. Those innocuous NAs scattered throughout your dataset represent a statistical minefield where one wrong move can introduce bias that ripples through every conclusion you draw. Now that we've designed our approach with the right tools, we enter the development phase of the EDI framework. This is where we implement practical solutions for the data problems we've identified. And perhaps no challenge in data preparation is more deceptively complex than handling missing values. What makes missing data so treacherous is that the standard solutions most tutorials teach, simply dropping incomplete rows or filling in gaps with averages, often introduce serious bias that can corrupt your entire analysis. These approaches might seem convenient, but they make a dangerous assumption that the data is missing completely at random. In reality, missing values typically follow patterns that, if ignored, can systematically skew your results. Before applying any solution, we need to investigate the pattern of missingness in our data. Are certain variables more likely to have missing values? Do these gaps appear randomly or do they cluster around specific conditions? Visualizing these patterns is the critical first step that many analysts skip. Let's look at a practical example. Imagine you're analyzing patient health data and notice that blood pressure readings are frequently missing for older patients. If you simply drop rows with missing values, you're systematically removing older patients from your analysis, potentially leading to conclusions that don't apply to this important demographic. Similarly, if you impute these missing values with the overall average, you're likely underestimating blood pressure for older patients, again introducing systematic bias. Here's how we can visualize missing data patterns using the Tidyverse. These visualizations reveal crucial insights about which variables have missing values and how these missing values co-occur across variables, essential information for choosing the right imputation strategy. After understanding the pattern, we need to select an appropriate imputation method based on both the pattern of missingness and our analysis goals. Let's explore the main approaches and when to use them. Mean or median imputation is perhaps the most commonly taught method, but it comes with significant drawbacks. When you replace missing values with the average, you're artificially reducing the variability in your data and distorting the original distribution. This can lead to underestimated standard errors and inflated test statistics, giving you false confidence in your results. Mean imputation might be acceptable as a quick exploratory step, but it's rarely appropriate for final analysis. It assumes missing values are randomly distributed across your dataset, an assumption that rarely holds in practice. Predictive imputation methods offer a more sophisticated approach. These techniques use the relationships between variables to make educated guesses about missing values. For instance, you might use a regression model to predict missing values based on other variables. Predictive imputation better preserves the relationships within your data, making it suitable when variables are correlated and missingness depends on observed variables. However, it can still introduce bias if the missing data mechanism is related to unobserved factors. For the most rigorous approach, we turn to multiple imputation. Rather than creating a single imputed dataset, this method generates several plausible versions of the complete data, each with different imputed values. You then analyze each dataset separately and combine the results. What makes multiple imputation powerful is that it accounts for the uncertainty inherent in guessing missing values. The variation across imputations reflects this uncertainty, leading to more honest confidence intervals and p-values. It's particularly valuable when dealing with data that's missing at random, where missingness depends on observed variables but not on the missing values themselves. But how do we know if our imputation strategy is working? Visualization plays a crucial role here too. We can compare the distributions of observed and imputed values to check for implausible imputations. If the imputed values follow a dramatically different distribution than the observed values, that's a red flag suggesting our imputation model may be inappropriate. For transparency and reproducibility, documenting your imputation decisions is essential. Your documentation should clearly state 1. The method used for imputation and the rationale behind this choice. 2. Any assumptions made during the imputation process. 3. The variables included in the imputation model. 4. The diagnostic checks performed to validate the imputation. Here's a template for documenting imputation decisions. This level of documentation ensures that others and your future self understand exactly what was done and why, enabling proper evaluation of your analytical decisions. The impact of imputation choices can be substantial. Consider a medical study where patients with severe symptoms were less likely to complete quality of life questionnaires. If the analysts simply dropped incomplete cases, they would systematically remove the most severely affected patients, potentially leading to overly optimistic conclusions about treatment efficacy. By properly modeling the missingness mechanism and using appropriate imputation techniques, they could have avoided this bias. Remember that imputation is not about fixing your data or making up values. It's about properly accounting for uncertainty and avoiding bias when analyzing incomplete datasets. The goal is to preserve the relationships in your data while honestly representing the limitations of what you know. With our missing data handled through predictive imputation, we now face a more insidious threat to our model's integrity. Ever noticed how a single unusual observation can completely change your regression line? I've witnessed million-dollar decisions based on analyses where no one questioned if extreme values were insights or errors. The most dangerous aspect of outliers isn't their existence, it's our inability to distinguish between valuable signals and statistical noise. When examining outliers, we're essentially playing detective, trying to determine if an unusual data point represents a genuine phenomenon or a measurement error. This distinction is critical because legitimate outliers often contain invaluable insights about edge cases or emerging trends, while erroneous values can completely derail your analysis. Think of it this way. Removing a legitimate outlier is like discarding a crucial piece of evidence at a crime scene, while keeping an erroneous value is like planting false evidence. The consequences of mishandling outliers ripple throughout your analysis pipeline. Keep erroneous values, and your models become skewed toward these anomalies, producing unreliable predictions when deployed. Remove legitimate extreme values, and you lose sensitivity to important edge cases that might represent your most valuable business opportunities. For instance, in financial fraud detection, the most unusual transactions are precisely what you need to identify. Treating them as errors to be removed would cripple your model's ability to detect actual fraud. So, how do we systematically identify these outliers? We need to move beyond simplistic approaches and employ a variety of complementary techniques. Let's start with univariate statistical methods, which examine each variable independently. The z-score method we discussed earlier works well for normally distributed data but falls short when your distribution is skewed or multimodal. Let's enhance our detection toolkit with a more robust approach that doesn't assume normality. Here's how we might implement the IQR method in the Tidyverse. But univariate methods only tell part of the story. A data point might appear perfectly normal when examining each variable independently, yet still be an outlier when we consider the relationships between variables. This is where multivariate outlier detection becomes essential. The Mahalanobis distance is particularly effective for multivariate outlier detection as it accounts for correlations between variables. Unlike simple distance metrics, Mahalanobis distance considers how variables move together, making it especially valuable for normally distributed multivariate data. For example, a house with both high square footage and high price might not be an outlier, but a small house with an extremely high price could be flagged by this method, even if neither the price nor square footage alone would trigger univariate detection. Here's how we might implement Mahalanobis distance detection in R. Visual inspection remains one of our most powerful tools for outlier detection. Let's explore some visualization techniques that can help us identify unusual observations more intuitively. Box plots provide an immediate visual indication of potential outliers, showing the distribution's central tendency and spread while highlighting points that fall outside the whiskers. A tidyverse approach might look like this. Scatter plots help us see relationships between variables and can reveal outliers that might be missed in univariate analysis. For multivariate data, heat maps can visualize correlations and help identify unusual patterns that might indicate multivariate outliers. But identifying outliers is only half the battle. The more critical question is, what should we do with them? This is where a decision framework becomes invaluable. When faced with an outlier, we should first determine its nature. Is it a legitimate extreme value or a data error? This assessment requires both statistical evidence and domain knowledge. For instance, in a housing dataset, a mansion priced at $10 million might be statistically unusual but perfectly legitimate, while a typical suburban home listed at $50 million likely represents an error. Based on this assessment, we have three primary options. One, remove the outlier if it's clearly erroneous or will significantly bias your analysis. Two, transform the variable to reduce the impact of extreme values. Three, keep the outlier if it represents a legitimate observation relevant to your analysis. Let's implement these strategies in Tidyverse code. Your decision should be guided by the specific context of your analysis. For predictive modeling focused on typical cases, removing or transforming outliers might improve performance. For anomaly detection or risk assessment, those same outliers might be the most valuable data points in your entire dataset. The impact of these decisions on model performance can be dramatic. Case studies have shown that improper handling of outliers significantly affects model results, leading to overfitting or underfitting and reducing reliability when the model encounters new data. A model trained on a dataset with unaddressed outliers may fail to generalize well beyond your training data. Whatever approach you choose, thorough documentation is essential. This ensures transparency and allows others to understand your rationale, enhancing reproducibility and trust in your analytical process. Consider documenting. 1. The methods used to detect outliers. 2. The criteria for classifying points as outliers. 3. The justification for your treatment approach. 4. The impact of your outlier handling on model performance. 5. any sensitivity analyses performed. A simple documentation template might look like this. While outlier detection helps us distinguish signal from noise, our features still speak different mathematical languages. Imagine two powerful predictors, one measured in billions and another in decimals, competing for your model's attention. Which one do you think will dominate the algorithm's decisions, regardless of its actual importance? This imbalance represents a fundamental challenge that can undermine even the most meticulously cleaned dataset. You've diligently handled your missing values, addressed outliers, and fixed structural errors, but without proper normalization, your machine learning models may still produce disappointing results. Normalization is the process of rescaling your features to ensure they contribute appropriately to model training, regardless of their original units or ranges. Think of it as establishing a fair playing field where each variable can demonstrate its true predictive power without being overshadowed by features that simply have larger numerical values. Let me illustrate why this matters with a practical example. Imagine building a house price prediction model with two features: property size in square feet, ranging from 1,000 to 5,000, and distance to the nearest school in miles, ranging from 0.1 to 5. Without normalization, the property size feature will exert a disproportionate influence on the model simply because its values are numerically larger, not because it's necessarily more important for prediction. This mathematical imbalance creates a situation where algorithms effectively pay more attention to features with larger scales. For gradient-based algorithms like neural networks and many regression techniques, this creates computational inefficiencies, slower convergence, and potentially trapped optimization. For distance-based algorithms like k-nearest neighbors, unnormalized features can completely distort the meaning of nearest neighbors. So how do we solve this problem? Several normalization techniques exist, each with specific applications depending on your data's characteristics and the algorithms you're employing. Min-max scaling is perhaps the most intuitive approach, transforming your data to a fixed range, typically between 0 and 1. The formula is elegantly simple: V, Vmin, Vmax, Vmin. This technique preserves the relative relationships between values while ensuring all features share the same scale. However, it comes with an important limitation: sensitivity to outliers. Since the transformation depends on minimum and maximum values, a single extreme value can compress the majority of your data into a tiny portion of the range, diminishing the contrast between non-outlier values. Standardization, also known as z-score normalization, takes a different approach. Rather than forcing data into a specific range, it rescales features to have a mean of 0 and a standard deviation of 1. The formula transforms each value using VMAS, where M represents the mean and ES the standard deviation. This technique works particularly well with normally distributed data and algorithms that assume normal distributions, such as linear regression and support vector machines. Standardization handles outliers more gracefully than min-max scaling, as extreme values will simply have more extreme z-scores without compressing the rest of the distribution. For datasets where outliers remain a significant concern even after detection and treatment, robust scaling offers a more resilient alternative. Unlike standardization, which uses the mean and standard deviation, both sensitive to outliers, robust scaling employs the median and interquartile range. The formula: V median IQR produces normalized values that maintain their distributional characteristics even when extreme values are present. This makes robust scaling particularly valuable for real-world data sets where perfect outlier removal isn't feasible. Some datasets present distributions that are fundamentally skewed. No amount of linear rescaling will make them approximately normal. In these cases, log transformations can be remarkably effective. By applying the logarithm function to your data, you can dramatically reduce the impact of extreme values and create more symmetrical distributions. This is particularly useful for features with exponential growth patterns or heavy right skews, such as income data, population figures, or certain physical measurements. The beauty of log transformations lies in their ability to compress wide ranges while preserving important relationships in the data. Let me demonstrate these techniques with code examples using the Tidyverse. The choice between these techniques isn't merely academic, it can dramatically impact your model's performance. For neural networks and gradient-based methods, standardization often works best, helping algorithms converge faster. For bounded algorithms like k-means clustering, min-max scaling ensures all features contribute proportionally. When outliers can't be fully addressed, robust scaling prevents them from dominating. And for highly skewed distributions, log transformations can reveal patterns that would otherwise remain hidden. Don't forget that categorical variables require their own form of preprocessing before most algorithms can use them effectively. The two main approaches are label encoding and one-hot encoding. Label encoding assigns a unique integer to each category, which works well for ordinal data with natural ordering, like small, medium, large. However, for nominal categories without inherent order, like colors or cities, one-hot encoding creates binary columns for each category, preventing algorithms from incorrectly inferring numerical relationships between categories. One often overlooked aspect of normalization is verification. After applying these transformations, how do you know they've worked as intended? Visualization provides the clearest answer. Histograms and box plots comparing distributions before and after normalization can reveal whether your transformations achieved the desired effect. For standardization, verify that the mean is close to 0 and standard deviation near 1. For min-max scaling, confirm all values fall within the expected range. This verification step is crucial because certain transformations may not work as expected with every distribution. For instance, attempting to standardize heavily skewed data won't produce a normal distribution. You might need to log transform first, then standardize. The impact of proper normalization can be striking. In a comparative experiment, a model trained on unnormalized data might achieve 60% accuracy, while the same model architecture trained on properly normalized features could reach 90% or higher. This performance gap reveals that normalization isn't merely a technical detail, it's a fundamental requirement for effective machine learning. This normalization stage forms a critical bridge between data cleaning and effective modeling. Think of it as translating your variables into a common mathematical language that your algorithms can properly interpret. Without this translation, your algorithms will struggle to extract meaningful patterns, regardless of how clean your data might be. Theories and isolated techniques are valuable, but the true challenge emerges when facing a dataset like the Guttmacher Institute's Pregnancies and Birth Rates collection, where missing values, inconsistent formats, and over 100,000 data points converge into what many data scientists secretly call the project killer. We've reached the implementation phase of our EDI framework. This is where theory meets reality, and all our carefully learned techniques are put to the test against genuinely messy data. The implementation phase isn't simply about applying solutions, it's about adapting them to unexpected challenges that inevitably arise when working with real-world information. Let's consider the Guttmacher Institute's pregnancies and birth rates dataset as our working example. This substantive dataset contains 104 columns spread across 1,000 rows of information spanning various age groups. At first glance, it might seem manageable, but dig deeper and you'll find a tangled web of data quality issues waiting to derail your analysis. When approaching a dataset of this complexity, the first step is constructing an end-to-end workflow that can transform raw data into analysis-ready information. This workflow shouldn't be ad hoc. It needs to be systematic, documented, and reproducible. Let's walk through what this looks like in practice. The workflow begins with importing the data. With the Guttmacher Institute dataset, you might use pandas in Python to read the CSV file. But real-world data rarely cooperates so easily. You might immediately encounter encoding issues, delimiter inconsistencies, or header problems. An improved approach integrates error handling and preliminary inspections. This immediate data inspection gives you critical information about what you're facing, like discovering that 30% of the values are missing or that dates are stored as strings instead of date-time objects. After importing, the next step is creating a systematic approach to tidying the data. With 104 columns, examining each one manually would be prohibitively time-consuming. Instead, you can build functions that automate repetitive tasks. You can then apply this function to all columns to identify the most problematic areas. This approach quickly identifies columns with high missing percentages, zero variance, or other issues that might warrant special attention or even elimination. For the Guttmacher Institute dataset, you'll likely discover inconsistent formats across multiple columns. Birth dates might be recorded differently based on region, numerical values might use varying decimal separators, and categorical variables might have inconsistent labeling. Rather than handling each issue separately, build modular functions for each type of problem. When implementing these functions, you'll often encounter unexpected issues. Perhaps some dates include time information while others don't, or some numeric fields have text annotations. This is where the iterative nature of data wrangling becomes apparent. You'll need to refine your functions as you discover new edge cases. For the Guttmacher Institute dataset with its 1,000 rows, these operations execute quickly on a standard computer. But what happens when you need to scale to millions of rows? This is where efficient data processing techniques become essential. One approach is to leverage data structures optimized for large data sets. For example, using pandas with Apache Arrow for memory-efficient operations. Another critical strategy is data aggregation, reducing the dataset size by summarizing information at an appropriate level of detail. With the pregnancies data, perhaps you don't need individual records, but rather statistics by age group and region. Feature selection can further reduce complexity by eliminating redundant or low-value columns. For truly massive datasets, distributed computing frameworks like Apache Spark become invaluable. Throughout this implementation phase, creating a library of reusable functions is essential for efficiency. Rather than writing one-off code, build a toolbox of functions that can be applied across different projects. These modular functions encapsulate common data cleaning tasks, enabling consistent application of techniques across different datasets. By combining them into a flexible pipeline, you create a systematic approach that can handle diverse data challenges. What if the very process meant to clean your data actually introduces new errors? You've written elegant code to transform the Gut Matcher Institute dataset, but a critical question remains. Did your transformations truly improve the data quality, or did they subtly distort it in ways that could undermine your entire analysis? This is where the evaluation phase of the EDI framework becomes essential. While most data scientists rush to analyze their freshly wrangled data sets, the professionals who consistently deliver reliable insights take a crucial extra step. They systematically verify that their data preparation efforts have actually achieved their intended goals without introducing new problems. Even the most meticulous data wrangling can inadvertently introduce subtle biases or distortions. Consider what happens when you impute missing values using a technique that works perfectly for normally distributed variables but breaks down with the skewed distributions in your dataset. Or when your categorical encoding unintentionally creates relationships between unrelated categories. These errors can silently propagate through your analysis, leading to conclusions that appear valid but are fundamentally flawed. The evaluation phase serves as your last line of defense against these hidden dangers. It's not merely a checkbox to tick, but a comprehensive assessment of whether your preparation has enhanced or compromised your dataset's analytical value. Let's examine the core metrics that form the foundation of any thorough data quality evaluation. Completeness measures whether all required data elements are present after your wrangling operations. This goes beyond simply counting missing values. It assesses whether the data contains all the information necessary for your specific analytical goals. After implementing your missing value strategy, you should verify that no critical patterns or relationships have been lost in the process. Consistency checks whether your dataset maintains logical relationships and uniformity across related elements. For instance, if you've standardized date formats across multiple columns, consistency verification ensures that temporal relationships still make sense. Births don't precede conceptions, and follow-up measurements don't occur before initial assessments. This metric is particularly important when working with datasets like the Gut Matcher Institutes, where relationships between variables carry significant analytical meaning. Validity confirms that your data conforms to defined rules and constraints after all transformations have been applied. This includes checking that numerical values remain within plausible ranges, categorical variables contain only legitimate values, and derived calculations produce results that make logical sense. For example, after normalizing pregnancy duration data, validity assessment would verify that no durations have become impossibly short or unrealistically long. The accuracy metric is perhaps the most challenging to assess, as it measures how closely your prepared data reflects true values. Without access to ground truth for comparison, you might evaluate accuracy indirectly by comparing your results against established benchmarks or by cross-validating with external data sources. When working with birth rate statistics, for instance, you might compare aggregated values against official public health figures to identify potential discrepancies. Beyond these core metrics, two additional factors often overlooked in data quality assessment are timeliness and relevance. Timeliness evaluates whether the data represents the appropriate time period for your analysis, while relevance ensures the prepared dataset actually addresses your research questions. Data that's perfectly clean but outdated or irrelevant to your analytical goals provides little value. Visualization techniques offer powerful tools for evaluating the impact of your data preparation. Rather than relying solely on summary statistics, comparative visualizations can reveal subtle changes in distributions that might otherwise go unnoticed. Side-by-side box plots provide immediate visual feedback on how your outlier treatments have affected the overall distribution of each variable. Overlaid histograms or density plots can highlight how imputation strategies have altered the shape of your data, potentially revealing artificial patterns introduced by your chosen methods. For instance, when comparing pre- and post-wrangling distributions of maternal age in the GoodMatcher dataset, a histogram might reveal that your imputation strategy has inadvertently created an artificial peak at the mean age, a telltale sign of naive mean imputation. This visual evidence immediately signals the need to revisit your approach before proceeding with analysis. Small-scale model testing provides another crucial evaluation strategy that too few data scientists employ. Before committing to full-scale analysis, run preliminary models on a subset of your wrangled data to ensure it produces reasonable and expected results. This approach allows you to catch potential issues early when they're less costly to address. This testing might involve training a simple linear regression model to predict birth weights based on maternal characteristics, then evaluating whether the coefficients align with established medical literature. If your model suggests that increased maternal age correlates with dramatically higher birth weights contrary to known medical findings, it may indicate problems with your data preparation that require further investigation. Documentation of data lineage and transformation decisions is not merely administrative busywork, it's an essential component of evaluation that enables reproducibility and transparency. Maintaining detailed records of data sources, transformation steps, and the rationales behind your decisions creates an audit trail that allows you and others to understand exactly how the final dataset was created. This documentation should capture not just what you did, but why you made each decision. Rather than simply noting imputed missing values using mean, document your assessment of the missingness pattern that led you to select that method, and any validation steps you performed to verify its appropriateness. This approach builds institutional knowledge that prevents future analysts from repeating flawed approaches or misinterpreting your results. Version control systems provide significant advantages in tracking changes throughout your data preparation process. By implementing these systems, you create snapshots at various stages of wrangling, allowing you to roll back to previous versions if evaluation reveals problems with your approach. This capability is particularly valuable when working with complex datasets like the GoodMatcher Institutes, where changes to one variable may have cascading effects on others. The evaluation phase should not be viewed as a one-time checkpoint, but as part of an iterative process. As you assess the quality of your prepared data, you'll likely identify issues that require revisiting earlier phases of the EDI framework. Perhaps your evaluation reveals that your outlier treatment was too aggressive, or that your categorical encoding created unexpected patterns. These discoveries prompt refinements to your approach, creating a feedback loop that progressively improves data quality. In team settings, peer review serves as a powerful evaluation mechanism. Having colleagues review your data preparation code and scrutinize the resulting dataset brings fresh perspectives that can identify blind spots in your approach. Someone unfamiliar with your assumptions might question decisions that seemed obvious to you, leading to more robust solutions. For sensitive analysis, consider implementing a formal review process where team members must sign off on data preparation steps before analysis proceeds. Cross-validation between different analysis approaches can provide additional confidence in your data preparation. If multiple analytical methods, each with different sensitivities to data issues, produce consistent results, it suggests your prepared data is robust. Conversely, if different approaches yield wildly different conclusions, it may indicate remaining data quality issues that require attention. To bring these concepts into practice, consider implementing a standardized evaluation protocol that incorporates automated quality checks alongside human review. Tools like Great Expectations or Deek can automatically verify that your data meets predefined quality expectations, flagging potential issues for further investigation. These automated checks can be supplemented with visualization reports that highlight key distribution changes and relationship alterations resulting from your wrangling efforts. Automated tools can catch many data issues, but they're blind to the most insidious data wrangling mistakes. What makes these errors particularly dangerous isn't their complexity, but their invisibility. They silently corrupt your analysis while everything appears to function normally, creating a false sense of security that can lead to catastrophic analytical failures. Think about it. When your code throws an error, you know something's wrong and can address it. But what about the errors that never trigger warnings? These silent corruptions operate beneath the surface, compromising your results while all your quality metrics suggest everything is fine. This is where even the most meticulous data scientist can stumble. Consider the everyday operation of silent type conversions. When Python or R automatically converts data types without explicit warnings, it can fundamentally alter your numerical calculations. Imagine you're analyzing patient temperature readings where some values were recorded with decimal points and others as integers. Your analysis environment might silently convert these mixed formats, potentially changing 98.6 to 98 for some patients, a critical difference in medical context that would completely invalidate your findings about fever patterns. The most troubling aspect: your code runs perfectly, your visualizations look reasonable, and nothing indicates a problem exists. These silent conversions are particularly treacherous because they occur at the intersection of programming convenience and analytical precision. Your analysis environment helpfully tries to reconcile different data types to keep your code running, but this helpfulness can destroy the integrity of your results. When working with financial data, for instance, automatic rounding during type conversions can introduce cumulative errors that might appear insignificant in individual calculations, but compound into material misstatements across large data sets. Another dangerous pitfall lurks in the handling of categorical variables, where improper encoding techniques create a subtle form of model leakage. This occurs when information from your test set inadvertently influences your training process. Consider a scenario where you're building a customer churn prediction model and encode categorical variables like subscription type across your entire dataset before splitting it into training and test sets. This seemingly innocent approach allows your model to see the distribution of categories in your test data, information it shouldn't have access to during training. The consequences are particularly deceptive. Your cross-validation metrics will show impressively high performance that crumbles when the model encounters truly new data in production. The model learns patterns specific to your test set rather than generalizable relationships. This type of mistake is especially pernicious because it creates overly optimistic performance metrics that can mislead stakeholders and lead to flawed business decisions. To avoid this, always split your data before performing any transformations that involve looking at distributions across the entire dataset. Beyond model leakage, inappropriate imputation methods represent another class of subtle errors that disproportionately affect specific subgroups within your data. Consider a healthcare dataset where older patients are less likely to complete certain medical tests. If you impute missing values using overall averages, you're effectively replacing missing values for older patients with measurements that better represent younger populations, introducing a systematic bias that could lead to healthcare disparities in your analysis. This bias doesn't just affect statistical accuracy, it can have real-world consequences when your analysis guides decision-making. To prevent this, you need to understand the patterns of missingness in your data and consider group-specific imputation strategies that preserve important differences between subpopulations. Simply checking overall distributions before and after imputation isn't enough. You must examine how your chosen methods affect specific subgroups and whether they maintain the authentic relationships in your data. Inconsistent handling of outliers represents yet another invisible threat to your analysis. Many data scientists carefully identify and address outliers in their training data, but forget to apply identical processing to their test data or production inputs. This inconsistency creates a fundamental mismatch. Your model learns patterns from data with one distribution, but must make predictions on data with a different distribution. Consider a retail sales forecast model where you've capped extremely high transaction values in your training data at the 99th percentile. If you don't apply this same capping in production, your model will encounter transaction values it was never trained to handle, potentially producing wildly inaccurate forecasts. The model may perform beautifully in cross-validation, where the same pre-processing was applied to both training and validation sets, but fail catastrophically when deployed. To address these hidden dangers, systematic validation approaches must become a core part of your data wrangling workflow. Statistical tests provide one line of defense. Comparing distributions before and after transformations can highlight unexpected shifts. For instance, a chi-square test can verify whether categorical distributions remain consistent after processing, while a Kolmogorov-Smirnov test can detect subtle changes in numerical distributions. Visual validation offers another powerful tool. Instead of relying solely on summary statistics, create side-by-side visualizations, comparing your raw and processed data. These visual comparisons can reveal distribution changes that might not trigger statistical significance, but could still impact your analysis. Consider creating visualization dashboards that automatically generate before and after comparisons for each data transformation step. Documentation serves as your final safeguard against these invisible threats. For every dataset transformation, document not just what you did, but why you did it, what assumptions you made, and what validation checks you performed. This documentation creates accountability and enables others or your future self to evaluate the appropriateness of your data preparation decisions. A particularly effective practice is to maintain a data decisions log that records each pre-processing choice along with its justification and validation results. This log becomes invaluable when unexpected results emerge later in your analysis, as it allows you to trace potential issues back to specific data preparation decisions. For mission-critical analyses, consider implementing a formal code review process focused specifically on data preparation steps. Have colleagues explicitly check for the common pitfalls we've discussed: silent type conversions, inappropriate imputation methods, inconsistent outlier handling, and improper categorical encoding. This peer review can catch issues that might escape your notice when you're deeply involved in the analysis. Creating reproducible data preparation workflows represents another best practice that helps prevent these silent killers. By structuring your data wrangling as explicit, documented steps that can be rerun from scratch, you create opportunities to validate your approach at each stage. This reproducibility allows you to isolate problems when they occur and verify that your solutions work consistently across different datasets. Thorough understanding of your data source is equally important in preventing these subtle errors. Maintain a clear picture of where your data originates, how it was collected, and what pre-processing it may have undergone before reaching you. This contextual knowledge helps you identify potential issues that might not be apparent from the data alone, such as measurement inconsistencies or collection biases. Consider implementing automated data quality checks that run after each transformation step. Tools like Great Expectations or DQ can verify that your data meets predefined quality expectations at each stage of your pipeline, catching problems before they propagate through your analysis. These tools complement human review by systematically checking for issues that might escape visual inspection. As we've explored throughout this video, systematic data preparation using frameworks like EDI isn't merely a good practice, it's the cornerstone of successful data science projects. Recent studies confirm that structured data wrangling approaches demonstrably improve outcomes with reduced errors and enhanced model performance across diverse applications. What's particularly encouraging is the evolution we're seeing in data preparation tools. The industry is shifting toward more automated, user-friendly solutions that make these critical processes accessible to a broader range of data professionals. This democratization of data preparation capabilities means that the systematic approaches we've discussed are becoming increasingly implementable for teams of all sizes. Remember, in data science, your results can only be as solid as the foundation they're built upon. By investing in systematic data preparation, you're not just avoiding problems, you're actively creating the conditions for success.